Hey friends, welcome to the YouTube channel all about electronics. So in the earlier videos of the electromagnetic theory, we learned about the vector algebra and the different coordinate systems from the electromagnetic perspective. So from this video onwards, let us start with the vector calculus. So as I said earlier, this vector algebra and the vector calculus is a mathematical tool which will help us in understanding the electromagnetic theory and the Maxwell equations easily. So as a first step in that, let us start with the line integral, surface integral and the volume integral, because that will help us in understanding the key concepts of the electromagnetics such as the Ampere's law and the Gauss law. So if we see this line integral, then it can be given as the integration of this A dot dl, where this A is the vector field and the dl represents the differential length. And here if you see, then this dl is also vector quantity. That means here, to find this line integral, first we need to find the dot product of this A and the dl. And as you know, this dot product of this A and the dl will be the scalar quantity. So once you perform the dot product, then it will be integrated over the specific limit. Likewise, this surface integral can be given as the double integration of this A dot ds, where this ds represents the differential area and once again it is also vector quantity. That means this ds also has the direction. That means here, if we take the dot product of this vector field and the ds and integrate it, then we will get the surface integral. And likewise, this volume integral can be given as A times dV, where here this dV represents the differential volume. So unlike this dl and the ds, this dV is the scalar quantity. So here, if this A is the vector quantity, then the result of the integration will be the vector quantity. For example, if we want to find the average fill inside the volume, then after the integration we will get the vector quantity. But most of the time, this A is the scalar quantity, and in that case, this volume integral can be given by this expression. So in that case, as the both quantities are the scalar quantity, so the result of the integration will be the scalar quantity. For example, if this A is the volume charge density, then if we integrate it over the volume, then we will get the total charge that is enclosed by the volume. And in that case, as you can see, it is the scalar quantity. So here, to find this line surface and the volume integral, first of all we should know that how to represent this dl, ds and the dv and how to find their direction. So here, as its name suggests, here this differential length dl represents the small displacement in the space. And if we see its representation or the expression, then that depends on in which coordinate system it is represented. So first of all, let us see its representation in the Cartesian coordinate system. So let's say in the Cartesian coordinate system, we have some point P and we are moving from the point P to the P dash. So in this direction, if we see the differential length, then this dl can be given as this dx times ax plus dy times ay plus dz times az. Because here if you see, then while moving from the P to the P dash, there is a displacement in all the three directions. So here, this dx represents the small displacement in the x direction. Likewise, this dy and dz represents the small displacement in the y and the z directions. So that is the expression of the differential length in the Cartesian coordinate system. So similarly, let us see how to represent it in the cylindrical coordinate system. So as you know, in the cylindrical coordinate system, the three coordinates are the rho, phi and the z. So among them, this rho and the z represents the distance, while if you see this 5, then that represents the angle. So in this coordinate system, the displacement in the rho direction can be given as the d rho. Likewise, the displacement in the z direction can be also given as dz. And similarly, if we see the displacement in the phi direction, then it can be found by the arc, because as you know, the phi represents the angle. So directly, we will not have the displacement in terms of the phi. So that's why it can be given by this arc. And as you know, the length of the arc can be given as the radius times angle. So in this case, the radius will be equal to rho while the change in the angle will be equal to d5. So we can say that the displacement in the phi direction is equal to rho times d5. And of course, all the three displacements will point in the increasing direction of the axis. So overall, the differential length in the cylindrical coordinate system can be given as this d rho times a rho plus rho d phi times a5 plus dz times az. So similarly, now let us see the expression of the differential length in the spherical coordinate system. So as you know, in the spherical coordinate systems, the three coordinates are the r, theta and the phi. So among them, this r represents the distance, while the theta and phi represents the angle. So here, the displacement in the r direction can be given as dr, while if you see the displacement in the increasing direction of the theta, then that can be given by the arc. And once again, here the length of the arc can be given as the radius times angle. So here, for this movement, the radius will be equal to r, while the change in the angle is equal to d theta. So we can say that here the length of the arc is equal to r times d theta, and therefore the displacement in the increasing direction of the theta is equal to r times d theta. Likewise, if we see the displacement in the phi direction, then once again it can be given by this arc. So in this case, if we see the radius, then in this xy plane, this radius is equal to rho, and the change in the angle is equal to d5. That means here, the length of the arc is equal to rho times d5. And as you know, this rho is nothing but the projection of the r on the xy plane. That means here, this rho is equal to r sine theta. And therefore, the displacement in the phi direction is equal to r sine theta times d5. So in this way, these are the three components of the displacement in the spherical coordinate system. And therefore, the differential length in the spherical coordinate system can be given as this dr times ar plus r d theta times a theta plus r sin theta times d phi times a5. So in this way, based on the coordinate system, we should use the suitable expression of the differential length. So similarly, now let us see the differential surface area. So here, first let us find the expression of the differential surface area for the Cartesian coordinate system. And to find that, let us take some cube in the Cartesian coordinate system. So in general, in any coordinate system, if we keep a one coordinate fixed and change the other two, then we will get a plane or the surface in the 3D space. So for example, if you take the surface of the cube, then here the x coordinate remains the fix, while the y and z are changing. So for this surface, if we see the differential surface area, then it can be given as this dy times dz times ax. Because here, the direction of this differential surface area will be normal to the surface, and it will always point in the outward direction. So in this case, it is pointing in the plus x direction. Therefore, when the x coordinate is fixed, then in that case, this differential surface area can be given as this dy times dz times ax. That means here, this ds represents the tiny area of this surface. And if we integrate it over the boundaries of this y and z, then we will get this entire surface area. So likewise, if we keep the variable y constant and change the x and the z coordinates, then we will get the sum plane in this direction. So for this surface, the direction of the differential surface area will be normal to the plane. And as I said, it will point in the outward direction. So for this surface, if you see, then the y coordinate remains the fixed, while the x and z are changing. So therefore, the differential surface area can be given as this dx times dz times ay, because here the vector which is normal to the surface is pointing in the plus y direction. So likewise, if we keep the z coordinate constant and change the x and the y coordinates, then we will get the surface in this plane. So for this surface, the direction of the vector that is normal to the surface is pointing in the plus z direction. And for this surface, if you see, then this x and y are changing while the z remains the fixed. And therefore, for the given surface, the differential surface area can be given as this dx times dy times az. Now here, although we have taken the top surface, but for the given cube, if we keep the z constant and change the x and y, then it can be also represented by the bottom surface, right? Because for the bottom surface also, the z remains the fixed while the x and y are changing. That means for this bottom surface also, the differential surface area can be given by the same expression. But here, the direction of the vector will be the opposite. Because as I said, for the differential surface area, the vector is always normal to the surface and it is pointing in the outward direction. So therefore, for the bottom surface, the expression remains the same, but because of the change in the direction of the vector, we will also have the negative sign. That means in this case, the vector is pointing in the negative z direction. But in general, for the Cartesian coordinate system, depending on the surface, these are the expressions of the differential surface area. And in fact, we can also find that from the expression of the differential length. So for example, if you want to find the differential surface area which is pointing in the z direction, then we will multiply the components of the differential length in the x and the y direction. That means we should multiply the components other than the az. And in this way, we can find the differential surface area. And likewise, we can also find the other two. That means if we just remember the expression of the differential length, then from that, we can easily find the differential surface area. And later on, we will also see that with the help of it, we can also find the differential volume. So similarly, now let us see the expression of the differential surface area in the cylindrical coordinate system. So as you know, in the cylindrical coordinate system, the three coordinates are the rho, phi and the z. So here, if we keep the rho constant and change the phi and z, then we will get this curved outer surface. So for this surface, the differential surface area can be found by multiplying the differential lengths in the z and the phi direction. So we know that for the cylindrical coordinate system, the differential length in the z direction is equal to dz. And likewise, the differential length in the phi direction is equal to rho times d phi. And as you know, the vector for this differential surface area will be normal to this surface. So in this case, it will point in the direction of the arrow. So we can say that when the rho is kept constant, then in that case, this differential surface area can be given as this rho times d5 times dz times arrow. So if you are not able to visualize it, then just remember that this differential surface area ds will point in the direction of the variable which remains constant. So in this case, that is equal to rho, and therefore it will point in the direction of the arrow. Similarly, if we keep the z constant and change the other two variables, then we will get this surface. So for this surface, the differential surface area can be found by multiplying the differential lengths in the rho and the phi direction. So we know that the differential length in the rho direction is equal to d rho, and similarly the differential length in the phi direction is equal to rho times d phi. And once again, this surface will point in the direction that is normal to this surface. So in this case, it will point in the z direction. That means the expression of the differential surface area is equal to rho times d5 times d rho times az. And likewise, suppose we have a cylinder, then for the constant z, we will also get the another surface, that is the bottom cap of the cylinder. So for this surface also, the expression of the differential surface area will remain the same, but in this case, the direction of the vector will be opposite and it will point in the downward direction. So due to that, here we will also have the minus sign. So this is the expression of the differential surface area when we keep the z constant. So likewise, if we keep the phi constant and change the other two variables, then we will get this plane. So in this plane, if you see the differential surface area, then that can be found by multiplying the differential length in the z and the rho direction. So we know that the differential length in the z direction is equal to dz, while the differential length in the rho direction is equal to d rho. So therefore, the differential surface area can be given as d rho times dz times a5. because this plane will point in the direction of the A5. So in this way, these are the expressions of the differential surface area in the cylindrical coordinate system based on the which variable is kept constant. And as we have seen, it can be easily found by using the expression of the differential length. So for example, if you want to find the differential surface area which is normal to the rho direction, then for that, we will multiply the other two components of the differential length. And in this way, we can easily find the differential surface area. So similarly, let us find the expression of the differential surface area for the spherical coordinate system. So in the spherical coordinate system, if we keep the r constant and change the theta and the phi, then we will get this outer surface. And for this outer surface, the differential surface area can be found by multiplying the differential lengths in the theta and the phi direction. So we know that for the spherical coordinate system, the differential length in the theta direction is equal to r times d theta, while the differential length in the phi direction is equal to r sine theta times d phi. And as we have seen, this differential surface will point in the direction of the arrow. So we can say that when the r is kept constant, at that time, this differential surface area can be given as this r square sine theta times this d theta times d phi times ar. Likewise, if we keep the theta constant and change the other two variables, then we will get this conical surface. And the differential surface area for the given surface can be found by multiplying the differential lengths in the r and the phi direction. So we know that the differential length in the r direction is equal to dr, and we have seen that the differential length in the phi direction can be given as this r sine theta times d phi. So that is equal to r sine theta times this dr times d phi times a theta, because this differential surface will point in the direction of the a theta. So likewise, if we keep the variable phi constant and change the r and the theta, then we will get this plane. So for this plane, the differential surface area can be found by multiplying the differential lengths in the r and the theta direction. So we know that the differential length in the r direction is equal to dr, and likewise, the differential length in the theta direction can be given as r times d theta, and this surface area will point in the direction of the a5. So in this way, based on the which variable is kept constant, we got the three expressions of the differential surface area in the spherical coordinate system. And as you have seen, each expression of the ds can be easily found by using the expression of the differential length. So in this way, we found the expression of the differential surface area in the three coordinate system. And using this differential surface area expression, we can find the surface integral over the given vector field. So similarly, now let us see the concept of the differential volume. So this differential volume represents the small volume in the 3D space. So if we integrate it over the given boundaries, then we will get the entire volume of the object. But here, unlike the differential length in the differential surface area, this differential volume is the scalar quantity, and it can be easily found by multiplying the three components of the differential length. So in the Cartesian coordinate system, this differential volume dV can be given as this dx times dy times dz. So similarly, in the cylindrical coordinate system, this is the expression of the differential length. So therefore, the differential volume in the cylindrical coordinate system can be given as this rho times d rho times d phi times dz. That means here, we have multiplied all the three components of the differential length all together. And likewise, in the spherical coordinate system, this differential volume can be given as this r square sine theta times dr times d theta times d phi. That means once again, here we have multiplied the three components of the differential length. And in this way, we can find the differential volume in the any coordinate system. So now, once we have the expression of this differential length, differential surface area and the differential volume, then we can easily find the line integral, surface integral and the volume integral. And first, let us see the line integral. So let's say we have some vector field A, and in this vector field, we are moving from the point P to the point Q. So this line integral shows the effect of the vector field along the path PQ. So to find that, we will take the small differential length along the path. And here, we will find the dot product of this field A with this differential length. So here, if the vector field is perfectly aligned along the path, then its contribution will be maximum. That means here, if the theta is equal to 0, then in that case, the contribution of this vector field along the path will be maximum. But if the theta is 90 degree, then in that case, this dot product will become 0. And in that case, we can say that the contribution of this A along the path will be minimum. So in this way, when we perform the dot product, then we will get the contribution of this vector field along the differential length. And if we integrate it over the entire length, then we will get the overall cumulative effect of the vector field along the path. So in the electromagnetics, suppose we are moving from the one point to the another point in the electric field, then with the help of this line integral, we can find the potential difference between the 2 points. So here, instead of the open path, suppose we have the enclosed path or the circular path, then in that case, this line integral can be given by this expression. So once again, here to find this line integral, we will take the small differential length along the path. And we will find the dot product of this vector field with the differential length. And now, if we integrate it over the entire closed path, then we will get the overall effect of this vector field while moving along this closed path. So this will be helpful in understanding the Ampere's law. So similarly, now let us see the importance of the surface integral. So once again, let's say there is some vector field A and we have some surface S. So here, the surface integral measures the flux or the amount of field that is passing through this area. And it can be given by the following expression, where here this ds represents the small differential surface area. And as we have seen, the vector of this differential surface area will be normal to the surface. So if the vector field is aligned with this normal vector an, then the maximum field will pass through the surface. But if the field is perpendicular to the an, then the no field will pass through the surface. And that can be defined by this dot product. So if we integrate this dot product over the entire surface, then we will get the total flux that is passing through the surface. So here, if you see the surface integral, then it is defined for this open surface. That means here, this surface is not enclosing any volume. So similarly, this is also another example of the open surface. That means here, if you see the outer surface of this hemisphere, then that is also example of the open surface because it is not enclosing any volume. But if we put a lid on top of it, then along with this lid, it represents the closed surface. Similarly, if we take the surface of the sphere, then it is also example of the closed surface because here it is enclosing the entire sphere. So here, if there is some vector field A, and if we want to find the total flux that is passing through this surface, then it can be found using this closed surface integral. Or suppose, if there is some source inside this volume, then by finding the total flux that is coming out of the surface, we can find the total charge that is residing inside the volume. And in the electromagnetics, it will be helpful in understanding the Gauss law. So that is the importance of the surface integral. So similarly, let us see the volume integral. So suppose we have a volume charge density, then using this volume integral, we can find the total charge that is enclosed by the specific volume. So in this case, this rho v is the scalar quantity. And therefore, after the integration also, the result will be also scalar quantity. But as I said, sometimes this quantity can also be a vector quantity. And in this way, with the help of the volume integral, we can find the total quantity that is residing inside the volume. So that is all regarding the line surface and the volume integral. And now, to understand it more clearly, let us take few examples. So in this question, we have been given this vector field A, and we have been asked to find the flux of this vector field A that is passing through this surface, which is given by the following expression. So first of all, let us see the surface, which is defined by this expression. So if you see over here, then the given vector field is given in the Cartesian coordinate. So in the Cartesian coordinate, first of all let us define the given surface. So in the Cartesian coordinate, if we see the three axes, then that will be equal to x, y and the z. So let's say this is the x-axis, this is the y-axis and this is the z-axis. So here this y is equal to 1. So let's say that is over here, and here if you see, then x is varying from 0 to 1 while z is varying from 0 to 2. That means here the range of the z is from 0 to 2 while the range of the x is from 0 to 1. That means here if we see this surface, then this is how it will look like, and here it will point in the y direction. That means this will be the normal vector to the surface. So for the given surface, if we see the differential surface area ds, then it can be given as this dx times dz times ay. And here the flux that is passing through the surface as can be given as double integration of this a dot ds. And here if we perform this a dot ds, then we will only get one term. That means here this a dot ds is equal to z times this dx times dz. And here if we see the range of the x, then it will vary from 0 to 1 while the y will vary from 0 to 2. That means here the flux that is passing through the surface S can be given as integration of 0 to 1 integration of 0 to 2 times z times this dx times dz. So further if we simplify it, then we can write it as integration of 0 to 1 times dx times integration of 0 to 2 times dz times dz. So here the integration of the dx will be equal to x and its limit will be from 0 to 1. Likewise, this integration of z will be equal to z square by 2 and its limit will be from 0 to 2. So if you put the limits, then the value will come out as 2. That means here the flux that is passing through this surface is equal to 2. So in this way, with the help of this surface integral, we can find the flux that is passing through the surface. So similarly, you can also solve this following example by yourself. So here if you see, then we have been given this vector field in the spherical coordinate system. And here, once again, we have been asked to find the flux that is coming out of the surface, which is defined by the following expression. So here, first of all, we should know that what is the surface that is defined by the following expression. So here if you see, then the r is varying from 0 to 4. So nominally, if r varies in some range and the theta and phi r varies from 0 to pi and the 0 to 2 pi, then we will get the sphere. But here if you see, then the theta is varying from 0 to pi by 2. It means that it indicates the semisphere. And here, if the phi varies from entire 0 to 2 pi, then we will get this entire semisphere. But if you see over here, then the phi is varying from 0 to 3 pi by 2. That means here, the given surface consists of only 3/4 of the semisphere. And this portion will not be part of the surface. So from the 2D perspective if we see, then here it will consist of only 3/4 and it will not consist of this last quarter. So in this case if you see, then this surface consists of the 4 different surfaces. The one is this outer one. Let's say that is equal to S1. So this outer surface is the outer shell of this semisphere. And once again, it will consist of only 3/4. Likewise, the second surface will be equal to this bottom disk. And likewise, if you see the third surface, then this will be this third surface. And likewise, this will be the fourth surface. So in this way, combining these 4 surfaces, we will get our total surface. So this S1 can be found by keeping this r constant and by varying the theta and phi in the given range. Likewise, this surface S2 can be found by keeping the theta as pi by 2 and by changing the r and the phi in the given range. So similarly, this surface S3 can be found by keeping the phi as constant and changing the r and the theta. So in this case, the phi will be equal to 0. And similarly, for this surface S4, the phi will be equal to 3 pi by 2. And in this way, for these 4 different surfaces, we can find the flux that is passing through the individual surfaces. And then after, by combining the individual fluxes, we will get the total flux that is passing through the entire surface. So try to solve this example by yourself and let me know your answer in the comment section. But I hope in this video, you understood the concept of the line surface and the volume integral in respect to the electromagnetics theory. So if you have any question or suggestions, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.